In our last video, we proved Egorov's theorem, the theorem that says that uniform conversions in a very large set is similar to conversions almost everywhere whenever we have a finite measure space. And using the fact that we were working on a finite measure space was essential for the proof. But is this hypothesis really necessary? That is what we will work on in this video. And before we start, let me remind you that you can support the channel in a few different ways. You can donate on Ko-fi, become a member on Patreon, or buy merchandise in our store. All the links are in the description of the video. We're going to work with two examples that show that this hypothesis is actually necessary, meaning that if we don't have it, then we might not have Egorov's theorem. So we're gonna work with two spaces that have infinite measure and a particular sequence that satisfy the hypothesis of converging almost everywhere, but that do not satisfy this condition over here. For the first example, we will consider x to be the natural numbers, the sigma algebra M to be parts of x, and the measure mu to be the counting measure. So given a set, mu of the set will give us the cardinality of the set. So let's think for a minute what it means to have the conclusion of the theorem, that for every epsilon there exists a set such that this happens. So the first thing we have is the measure of the set is less than epsilon. Now since this happens for every epsilon, in particular it would happen for epsilon positive but smaller than 1. So if we have some set E in our sigma algebra such that the measure of E is less than epsilon, then because this is the counting measure, so this is actually just the cardinality of the set E, then having cardinality between 0 and 1 implies that the cardinality of the set is actually 0, because you can't have a fractional amount of elements in your set. And having 0 elements implies that E is actually the empty set. Also notice, and I didn't say this before, that the measure of x in this case is the cardinality of the natural numbers, which is obviously infinite. So we are not working with this hypothesis. So what we just said is, if the conclusion of this theorem is true, then it will give us uniform conversions on E complement, and in this case, E complement will be the entire space. So if some sequence converges to F on E complement, that implies that it just converges uniformly everywhere. So now the conclusion of our theorem is quite strong. It's telling us that in this space, if the theorem was true, then almost everywhere converges would imply uniform conversions. So let's take some particular sequence. We can define Fn of x to be the characteristic of the set 1 up to n. Now because this x is just a natural number, then the plots of our functions are a bit weird. They're not continuous, but that's fine. So we have 1, 2, 3 and so on, all the natural numbers. F1 would just be this number here. F3 would be these 3 points. And so on. We can see that pointwise our sequence is just converging to having all the points selected. So pointwise Fn is going to the function constantly 1. But it's not difficult to see, and I will leave this as an exercise. This sequence of functions does not converge uniformly to 1. That's also easy to see just by looking at the plot. So the value of n that we'll have to take, it obviously depends on the points x in the domain. So for this case, Egoroff theorem does not hold. But okay, this was a very odd space. It had this particular property that whenever we took a set with small measure, immediately that set would have to be the empty set. So we may ask ourselves if this behavior is only natural to these spaces where we don't have sets of arbitrarily small measure. We only have sets that go from measure 0 to 1. But in the following example, we'll see that no, that this happens in more general spaces, and we'll work on the space that we know best. For the second example, we're going to work with the set x to be 0 infinity, and the measure mu to be Lebesgue measure. So now the sigma algebra will be the sigma algebra of Lebesgue measurable sets in the 0 infinity. And we're going to consider the following sequence of functions. Fn is going to be the characteristic between n minus 1 and n. We have worked in a previous video with a similar sequence, so if you haven't, make sure you check that one out first. Let's see what this sequence looks like. We start with f1, that's going to have the value 1 between 0 and 1, and it's going to take value 0 for any other number. Because I'm in 0 infinity, I'm only worrying on positive numbers. So this is f1. f2 is going to have value 1 between 1 and 2, and 0 at any other number. f3 is going to have value 1 between 2 and 3, and 0 at any other number. And so on. We can see that this function is kind of shifting this interval to the right. So if I fix some point x, there will be some point onwards for which my sequence will always have value 0 at x. So that shows that fn goes to 0 pointwise. And it's easy to see from the plot that this convergence is not uniform. But Egorov's theorem is not saying that we have uniform convergence. It's saying that we might have uniform convergence on a large set. So it's a bit weaker than uniform convergence, and just by looking at the plot, I can't tell if this is true or not. That is, for every epsilon, is there a set for which the set itself has small measure, but I have uniform convergence in its complement? Well, I can't tell from the plot, so maybe we can assume that we do, and try and get some contradiction. So what would happen if we had some set E such that my sequence converges uniformly to 0 on the complement? What does this mean? Well, the definition of uniform convergence says that for every, let's say delta, so that I don't use epsilon again, there exists some natural number n such that for all n greater than or equal to this number n, and for all x, in this case we have conversions only on E complement, so for all x in E complement, fn of x minus 0 is less than delta. So if this was true, in particular it would be true for delta equals 1. So there would exist some natural number n, and this only depending on delta, not on x, such that for all numbers n greater than or equal to n, and for all x in E complement, fn of x is less than delta, so in this case less than 1. But now our sequence of functions are all characteristics, so actually fn of x is only taking two values, 0 and 1. And so if my sequence fn is less than 1, this implies that fn of x is actually 0. This happens for all n greater than or equal to n and for all x in E complement. Our function takes the value 0, but recall that fn is just the characteristic in n-1 n. So if it has value 0, that means that x does not belong to the interval n-1 n. And this is for all n greater than or equal to n. So there are many intervals that x doesn't belong to. Starting from capital N, it does not belong to capital N-1 n. But also when we move forward one more number, x is not in n plus 1, and so on. So these intervals are all just not belonging to this union, is not belonging to the interval n-1 infinity. So I took x in E complement and I showed that x is not here. Remember that the space where we are working is just the 0 infinity. So if x is not in the interval n-1 infinity, then x can only be in 0 n-1 open. So if x is in E complement, x is in this interval, that is just an inclusion of sets. E complement is a subset 0 n-1. And now taking complements on both sides, we get that the complement of this, n-1 infinity, has to be a subset of E, of the complement of E complement, which is E. So this is an interval that with Lebesgue measure has infinite length, and it's a subset of E. This tells us that E cannot have small measure. With this, what we have is that Egorov theorem does not hold. Going back to the theorem, the reason in both cases why it didn't hold is because this hypothesis of having a finite measure space is necessary.